You know that feeling when you're looking at data from, say, three different groups, and you're wondering, are the differences I'm seeing real, or is it all just random chance? Well, that is the exact problem we are going to tackle today with an incredibly powerful statistical tool called ANOVA. That's short for Analysis of Variance.
So here's our game plan. We're going to start with a classic researcher's dilemma, then introduce our hero, ANOVA, and meet its family. After that, we'll dive into the secret sauce of how it works, this idea of signal versus noise. And finally, we'll figure out what to do once you've actually got a result. Let's jump in. All right, so let's set the stage. The core problem ANOVA solves is something researchers face all the time. You've run an experiment with a few different groups, and you really need to know if the thing you did actually made a difference. Let's make this real. Imagine you're an educator, and you've just come up with three awesome new teaching methods. You run a study, you collect all the test scores, and now you're staring at the data. The big question is, how do you prove with actual statistical certainty if one of your methods is genuinely better than the others? So you plot it out, and right away, your eyes are drawn to method B. I mean, look at it. That bar is clearly the highest. It looks like the winner, right? But here's the catch. Is that difference really big enough to matter? Or could it just be a random fluke? This is where just looking at a chart isn't enough. We need something more powerful to tell us if that difference is what we call statistically significant. And that's where our hero of the day comes in, ANOVA. It's the tool that's designed to take us from a simple visual guess to a confident, statistically backed answer.
It sounds a little fancy, analysis of variance, but at its heart, it's just this: a formal way to check if the average scores, what statisticians call the means, of three or more groups are truly different from each other. It is an absolute cornerstone of experimental research for exactly this reason.
Now, you can't just throw any old data at ANOVA and hope for the best. There are a few rules of the road, or key assumptions, you have to follow to make sure your results are valid. Basically, your data should have a nice bell curve shape, the amount of spread within each group should be roughly the same, and, of course, the groups have to be independent of one another. Think of it like a pre-flight checklist before you can take off with your analysis. It's also super important to know that ANOVA isn't just a single one-size-fits-all test. No, it's more like a family of tests, and each one is designed for a slightly different kind of research question. Let's meet the key members of the family.
Okay, so which one do you use? Well, it all depends on your experiment. A one-way ANOVA is perfect for our teaching method example because we only have one variable we're looking at. But what if we wanted to see if the methods work differently for, say, 9th graders versus 10th graders? Now we have two variables, so we'd use a two-way ANOVA. And if we tested the exact same group of students multiple times, like before, during, and after a course, that's a job for our repeated measures ANOVA.
So how does ANOVA actually pull this off? How does it look at all these numbers and decide if the differences are real? Well, the secret lies in this really beautiful and simple concept. It's all about comparing the signal to the noise in your data. This right here is the absolute heart of it all. Everything boils down to this one question. ANOVA basically puts two things on a scale. On one side, you have the differences between the average scores of our teaching methods. And on the other side, you have the natural, random jungle of scores you'd expect to see within any single one of those groups. And this whole comparison is captured in one beautifully elegant formula. It's called the F ratio, and it is the engine that drives the entire analysis. And look how simple it is. It's just the variation between your groups divided by the variation within your groups. That's it. Let's think about it like this. The signal, that's the difference we're hoping to find. That's the effect of our different teaching methods. The noise is just the background static, the natural differences between students. If our signal is way louder than the noise, we get a big F value, and that's a huge clue that our teaching methods really did have an impact. Okay, so you've crunched the numbers, you've run the analysis, and now you have your F value. Great. What in the world does it actually tell you? Let's walk through how to make sense of the results. The process from here is actually pretty straightforward. That F value you calculated gets converted into something called a p-value, and the p-value is the real star of the show. It tells you the probability that you'd see the results you got if there was actually no real difference between the groups. We then compare that p-value to a cutoff we decide on beforehand, which is almost always 0.05 or 5%. And if your p-value is less than 0.05, that is the aha moment. That is the statistical green light you've been waiting for. It means the differences you're seeing are super unlikely to be just a random fluke. You can finally, confidently say that yes, there is a significant difference somewhere among your teaching methods. But, and this is a really important but, the ANOVA result is a bit of a cliffhanger. It's like a fire alarm going off. It tells you, hey, something interesting is happening over here. It confirms there's a difference somewhere, but it doesn't tell you if method B was better than A or if C was different from B. It doesn't pinpoint the difference. So to solve that final piece of the puzzle, we turn to something called post hoc tests. These are follow-up analyses that you only run after you get a significant ANOVA. They act like a magnifying glass, going in and comparing each pair of groups, A to B, B to C, A to C, to tell you exactly where the significant differences are hiding. So you see, ANOVA itself doesn't actually give you the final answer. It just tells you that there's a story in your data that's worth investigating. It gives you the big headline, but it's the post hoc tests that give you all the juicy details. And that leaves us with the real question every researcher has to ask. Now that you know there's a difference, what story does your data really want to tell?